Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is third lecture for the ninth week of wireless and mobile communication. We are having the topic of modulation techniques for different mobile radio communication channels. In our last lecture, we talked about linear modulation techniques, and we discussed that these are linear modulation techniques because the amplitude of transmitted signal varies linearly with the modulating signal. In most cases, these linear modulation techniques can be modulated signals. They can be represented as two components, cosine components and sine components, or for short we sometimes write those components as I and Q components. The common examples for linear modulation techniques are BPSK, which is the basic form of PSK signaling, where we use two different phases to represent the binary information. We discussed QPSK in our last class, in which we use four different symbols, and we use four different phases to represent those four symbols. So QPSK is actually an M array version or 4 array version of BPSK. A variant of QPSK is named as offset QPSK. This is called offset QPSK because the two symbols, two bits in the QPSK symbols, they are offset by half of the symbol duration. By offsetting these two bits, we ensure that the maximum change in the phase at one time is only 90 degrees. So at any instance the phase change does not exceed 90 degrees. So we continue our discussion on to this linear modulation technique. The next modulation technique is known as differential phase shift keying, or DPSK. DPSK is actually is only PSK technique in which we do not need synchronization for detection purposes. So this can be detected non-coherently, that is without any phase information from the transmitter. We can detect the DPSK signal. For DPSK, the information is not encoded in the absolute phase of the wave, rather it is encoded in the phase change. So different bits in the DPSK scheme are represented by different amount of phase change. So phase shift gives you the information related to the bits. Say for example, we talk about the binary differential phase shift keying, DBPSK, and we say that the binary 1 is represented by a phase change of 180 degree, whereas the binary 0 is represented by no phase change, or you can say 0 degree phase change. So you can see in the waveform here, this one is followed by another one. Since the next bit is 1, you would see a phase change of 180 degree here. But when the next bit is 0, there is no phase change. The previous phase continues, and this continued phase represents that the next bit is 0. Similarly, for since the next bit is also 0, you do not see any phase change here as well. Similarly, since the bit is 0, we do not see any phase change. And as the next bit comes out to be 1, so you would see a phase change of 180 degree here. You can see that there is a phase change of 180 degree. So this change in phase represents that the bit is 1. Similarly, when next bit is 1, you would see that there is a phase change of 180 degree. So at the receiver side, receiver has to detect the difference of phase. Instead of absolutely measuring the phase, it only needs to detect how much phase changes at the bit duration, and if there is no phase change, in that case the receiver will decide it as 0. And if receiver finds that the phase changes at that bit duration, so eventually the receiver will decide it as binary 1. Similar information can be encoded at higher array systems, M array systems. For example, for 4 array system, so if you have differential QPSK system, in that case again the information would be encoded by a phase change, but now there will be 4 possibilities of phase changes. Say for example 1 is represented by no phase change, so you do not see any phase change in 1. When this 0 you would see a phase change of 180 degrees. So 180 degree phase change represents that the next 2 bits are 0. For bits of 10 you would see a phase change of 90 degree. So 90 degree phase change reflects that the bits are 0 and 1, and 10 corresponds to the phase change of 270 degree. So 270 degree phase change would represent that the next 2 bits are 1 and 0. So this is the differential phase shift keying. Sometimes we use higher order modulation schemes as well, which are generally named as QAM, which is abbreviation for quadrature amplitude modulation. For quadrature amplitude modulation, we do not rely on the phase change only. In fact, we change the phase as well as the amplitude of the signals as well. Say for example, we have a 16 QM signal here. This diagram represents the 16 QM signal. If you see any symbol which is represented by a dot here, so the distance from origin, this distance represents the amplitude, and the angle from this I-axis this represents the phase. So this symbol, you can see this one and this one, these two have same amplitude but they differ in phases. So receiver will have to decide on the amplitude as well as the phase in order to decide the symbol. Similarly, if we compare this symbol with this one, previous one, so this symbol and this one, they have the same phase but they differ in amplitude. Similarly, if you look at some other symbols, say for example this one, and compare it with this one, so these two may have different amplitudes, same amplitudes, but they would have different phases. But this one compared with this one may have same different phases as well as different amplitudes. So in order to decide the symbols at the receiver side, we not only need to decide the phase as well as the amplitude. At the right side we have a constellation of 64 QM symbol, 64 QM symbol. So there are 64 total possible symbols, and you can see that each symbol has different phase as well as different amplitude, and in order to decide any symbol at the receiver side, we would be needing the information of amplitude as well as the phase. So this concludes our discussion onto the linear modulation schemes, which has different types, and we briefly discuss different types of linear modulation scheme. Let us now move on to the non-linear modulation schemes, which are referred to as constant envelope modulation scheme. These are called non-linear because the amplitude of the waveform it does not change with the modulating signal. So in general the amplitude remains constant. Many practical mobile radio communication systems, they use this type of modulation scheme where the amplitude remains constant regardless of any variation in the modulating signal. So in that case the information need to be encoded in the frequency rather than amplitude. So these schemes they refer to a type of frequency modulation. There are certain advantages related to these constant envelope modulation schemes. First of all, these are non-linear schemes, so we can use non-linear amplifier for the power amplification purposes, and these non-linear amplifiers they are very power efficient, and they provide good power efficiency to the system. Second big advantage of using such a scheme is that these non-linear amplifiers, they provide a low out of band radiations. So because of the low out of band radiation, we generally do not see a significant amount of effect of interference coming from co-channels and adjacent channels. These modulation schemes enable us to have a relatively simpler receiver designs. In most cases, as the amplitude is constant, so these schemes, they have higher immunity to the noise, because noise causes variation in the amplitude, and for these type of schemes the information does not relates to the amplitude of the signal. So therefore variation in that amplitude because of noise does not affect the information contents in the signal, and those variations can be removed by using simple limiter discriminator circuits at the receiver sides, and this provides a good immunity against the noise and signal fluctuations because of the fading effects. However, there are certain disadvantages associated with this type of scheme. First of all, these constant envelope modulation schemes, they require relatively larger bandwidth as compared to the linear modulation scheme. Secondly, they are not very useful when power efficiency is very crucial. So the most basic type of this constant envelope modulation scheme is binary phase shift keying. So for binary phase shift keying, we use two different frequencies to represent waveforms or digital data. So for example, these pulses are representing data. So this is binary 0 and this is binary 1 and this is binary 0. The gray area represents the 1 and the white area represents binary 0. So when we modulate this binary data onto a frequency modulated system, so in that case the binary 1 is represented a relatively higher frequency of the carrier, and the binary 0 is represented by a relatively low frequency of the carrier wave. So carrier frequency gets changed as we change the information. So binary systems, they represent the binary information is represented by different frequencies in the system. So there is a constant difference which is the offset from the nominal carrier frequency exists in the representation of binary systems. We can have higher order FSK systems, M-array FSK systems. In that case, we would be needing more frequencies in order to represent more number of symbols. Another common scheme of FSK is named as minimum shift keying. It is actually a modified version of minimum shift keying. First of all, in this minimum shift keying, it is ensured that the frequencies are shifted in such a way that the phase remains constant. So at one in FSK, it is possible that you may have different phase for one carrier for one symbol. For example, for binary 1 may have a different phase and binary 0 may have a different phase, but for MSK the phase remains the constant. So it's a continuous change in the phase whenever the shifting is done between different symbols. So this is a type of continuous phase shift keying. Secondly, the frequency deviation which is possible, which is used in this MSK is 0.25 of FM, where FM is the maximum modulating frequency. This 0.25 FM corresponds to the modulation index of 0.5. Actually, this modulation index of 0.5 relates to the minimum frequency spacing where we can detect two different symbols. So this scheme is named as minimum shift keying because it is based on a minimum frequency spacing. So it is an FSK scheme where we use the change in frequency and in such a way that it is the minimum possible value, and this signal has to be detected coherently and orthogonally. So this is the minimum spacing which ensures the orthogonal signals, and also we need to detect coherently. You may remember that the FSK can also be detected non-coherently, but MSK has to be detected coherently. So because we are using the the minimum possible value of frequency deviation, therefore this scheme is generally very bandwidth efficient for orthogonal detection. MSK is sometimes referred to as fast FSK. The reason is that it is relatively fast. The frequency spacing is small as compared to the conventional non-coherent FSK. In fact, this frequency spacing is only one half of the conventional non-coherent FSK scheme. MSK, as I said, is because it's using lesser frequency, is spectrally more efficient, and there are certain other advantages related to this scheme as well. This has a constant envelope, so it's a non-linear scheme, as I discussed previously. It's a specific, it has a better spectral efficiency. It has a good BR performance, so generally the error probability is low in this scheme, and it also has a good self-synchronization capability. Another variant of minimum shift keying is actually named as Gaussian minimum shift keying, or GMSK. GMSK is actually the MSK system, but used with a Gaussian pulse shaping filter. So before applying the signal to the modulator or minimum shift keying modulator, we use a pre-modulation Gaussian filter, which also improves the overall spectral efficiency of the system by suppressing the side lobes of the system. So this GMSK system has even smaller amount of side lobes, and this is more power efficient and good spectral efficiency. And because of these characteristics, this GMSK modulation scheme was used in GSM standard. So the modulation scheme used in the GSM standard was the GMSK scheme. Okay, now we move on to the new type of scheme, which is named as spectrum modulation techniques. The linear and non-linear modulation techniques that we discussed so far, there was a common property regarding that we were focusing on reducing the bandwidth of the signal. So we intend to have the modulation scheme which provides a good efficiency with smaller amount of bandwidth. But for this new type of scheme, which is used in third generation onwards, we use a spread spectrum technique, which actually uses a bandwidth which is several orders wide as compared to the signal bandwidth. So this technique is based on having a wide band signal instead of having a relatively narrow bandwidth. So if we look at the single user, this system would be a very bandwidth inefficient, because we will be using a large amount of bandwidth. But the advantage we get from this spread spectrum technique is that we can accommodate a large number of users within the same band. So that large amount of bandwidth would be shared by many different users without significant interference. So when we have a multi-user system, in that case this spread spectrum system becomes very bandwidth efficient, although one of the user is using a large amount of bandwidth. But because of the many users accommodated in the same bandwidth, we get overall advantage in the bandwidth efficiency. So how does this spread spectrum modulated signal works? So these signals, they are actually pseudo-random signal. So they have properties just like noise. If we compare the signal with the digital data, so this spread spectrum signal would appear as it is a noise signal. So how does this noise signal is generated? So modulating signal is spreaded in the frequency domain by using a pseudo noise sequence or a pseudo noise code, PN code. So this spreading is done using a PN code. This PN code is actually a binary code which although it appears random, but it is reproduced in a deterministic manner so that whenever a receiver needs, it can reproduce the signal. So this PN code is actually reproduced, is a random code which is reproducible by the receiver. This pseudo-random code has a property of having very small amount of cross correlation with other types of pseudo-random code. So if you have, say for example, if you have 10 different users, and what we do, we assign 10 different pseudo-random codes to each of the user, and those pseudo-random codes, they spread the signal into a larger bandwidth, and all of the 10 users, they share the same bandwidth. But when the receiver tries to recover the original signal, it calculates the cross correlation with the received signal using the same pseudo-random code. So the one which matches with the original transmitted code, it would have high cross correlation, and all others would have very low cross correlation. So the receiver can extract the desired signal by appropriately calculating the cross correlation, and all other users, or 9 users out of those 10, so one would be intended which will be recovered, and the other 9 users, when the cross correlation will be calculated with those that would have a very low cross correlation, so those signal will appear like noise to the received signal. So this cross correlation actually de-spreads the sequence when you cross correlate with the correct pseudo noise sequence. In that case, the signal is de-spreaded, and we restore the original modulated message in the same narrow band as was the original data, and all the undesired users, they result in a small amount of cross correlation. Eventually these signals, they appear like a wideband noise to the receiver output. So what are the important properties of this spread spectrum modulation techniques? So first of all, this spread spectrum technique has inherent interference rejection capability. So it is one of the important property. As I said, in order to extract the signal, we need to calculate cross correlation with the pseudo noise sequence, and only the correct pseudo noise sequence results in a higher cross correlation and recovery of the signal. and all other signals, they would only appear like noise. So other signals, although they are present in the same frequency band, they do not cause interference uh, to the original signal. Secondly, as we are using the same frequency band to accommodate all the signals here, so spectrum is basically shared among all those users. So we do not need any specific type of frequency planning. As if you recall, in our initial lectures we had a detailed discussion on the frequency planning as well, which is an important aspect of cellular system planning. But for this spread spectrum technique, we do not require that frequency planning. We just need to have orthogonal pseudo noise codes for each of the user, so that they result in the small cross correlation whenever you have a different code. Third thing is that these spread spectrum modulation techniques, they are resistant to the multipath fading. You can think of these signals as a wideband signals, because when a pseudo noise code is applied to the system signal, so it would become a wideband signal, and these wideband signals, they are generally frequency selective, and whenever they pass through any channel, and if there is a effect of fading, so particularly that fading affects the specific band of that wideband signal, so it does not affect the entire signal, it would only affect the small portion of the entire signal, and when it's despreaded, so that effect in the small portion would become insignificant. Also, the multipath effect, they are eliminated in these spread spectrum techniques, because these pseudo noise codes, they have another property, that if you calculate the correlation with the delayed version of the same pseudo noise code, so even in that case it will generate a low cross correlation. So whenever this correlation is calculated with the delayed version or the multipath component of the signal, so it will result in a small amount of correlation. Eventually that will be ignored by the receiver. So receiver will take only those components which has a relatively high correlation. Although there is a lot more detail related to spread spectrum techniques, but at this stage we only restrict our discussion to the basic introduction to the spread spectrum technique. I just want to conclude the discussion on defining two major categories of these spread spectrum techniques. There are two different categories of spread spectrum modulation scheme. One is called direct sequence or DS spread spectrum. In direct sequence, the pseudo noise code is directly multiplied to the baseband data. So baseband pulses are multiplied by the signal pseudo noise sequence, which is generated by a pseudo noise code generator. A single pulse in that pseudo noise waveform is named as a chip. So these chips, when they multiply to the baseband signal, they cause spreading of the signal in the frequency domain. So we get a wideband frequency signal after multiplying this pseudo noise sequence to the baseband signal. The second category of spread spectrum modulation technique is named as frequency hopped spread spectrum technique. In frequency hopped spread spectrum technique, actually we have periodic changes in the transmission frequency. So this frequency hopped or FHSS technique can be regarded as a sequence of modulated data burst with time varying pseudonoid random carrier frequencies. So instead of having a random sequence, we have different random carrier frequencies, and those frequencies are used to modulate the data in order to have a broadband or wideband signal. And similar to that PN sequence, the same pseudo random frequencies need to be used at the receiver side in order to calculate the correlation and recover the original signal. The set of possible carrier frequencies is called the hop set. So the frequencies that are used in any FHSS scheme, they are named as hop set. Okay. So this was an introduction on spread spectrum modulation technique, which is now have become very popular because of the properties that we discussed in the previous slide. So with this we move to the last topic of our discussion, which is the modulation performance in fading and multipath channel. Generally we have different modulation schemes, and these schemes they perform differently for different types of channel. We use different performance metrics for calculating the performance of different schemes, or in order to compare different types of schemes. A common performance metric is named as bit error rate, or BER, which is actually the probability of having a bit in error. So whenever we are comparing two different schemes, so we compare on the basis that how much bit error they are generating at a specific amount of EB by N naught. Another important parameter that we use to specify the performance of a modulation scheme is the probability of outage. Probability of outage refers to the condition where we cannot have a quality communication in that particular type of system. Actually, this outage event is specified when we have a specific number of errors occurring in a given transmission. Say for example, if our data group has been sent and we get, say for example, our event is that we have errors more than 10%, in that case we may not be able to have a reliable communication. So whenever we have errors which are greater than the 10% of that that particular data bit in that data group, we would say that this is an outage event, and we would have a certain probability of outage. And of course a better system would be one where we would have a smaller amount of probability of outage. These bit error rates and probability of outages, they are calculated analytically as well as through computer simulations. So there are different results. Just for comparison purposes, let me show a simple result of bit error rate performance versus bit error rate performance of different modulation schemes. So these are FSK non-coherent detection, FSK coherent detection, DPSK and PSK. You can see that the horizontal axis represents this EB by N naught, and the vertical axis is representing the BER. And the common trend is that when we increase this EB by N naught, that means if we increase the bit energy, in that case the probability of error goes down. You can see that the FSK scheme and for non-coherent detection, it has the highest amount of error. DPSK and coherent FSK, they exhibit almost same amount of errors, but the PSK scheme perform better because it relates to the relatively smaller amount of bit error rate as compared to the other scheme. However, you must note that these are not the only characteristics of the system, as I previously mentioned as well, that there are certain other parameters that need to be considered when we are designing a system. For example, if we are comparing these two, so non-coherent FSK is the simplest, uh, has the simplest receiver, it's the simplest implementation because it's non-coherent, so it does not require any type of synchronization, so it does not need any synchronization circuitry. Secondly, this is FSK, so the information is represented in frequencies. So at the receiver side, what you need, you only need to have is, the band pass filters of a specific band in order to extract the original information. PSK on the other side, which has the best performance, it has relatively complex circuitry because it cannot be detected non-coherently. You need to have a synchronization circuitry in order to have recover the PSK information from the signal. So this is a simple comparison, and similar comparisons can be made for other types of schemes as well. And in fact, if you look at the book, other curves are also available for different scenarios, because this is only one scenario where we have relay and flat feeding channel. Similarly, for frequency selective feeding channel, this the performance would be different, and similarly for slow and fast channel, you may have different results, which are also presented in the book as well. But for the discussion here, in order to give you an idea, so I think this curve is enough to represent how we compare the performance of different modulation schemes and how they perform in a specific type of environment. So with this, we conclude our discussion on the modulation schemes for mobile radios. In this week, the 3 lectures in this week, we have covered different types of modulation schemes, and we tried to discuss the various aspects associated with those modulation schemes. So with this, we conclude this chapter here, and we will be starting a new topic in our next week's discussion. Thank you all.